Okay, welcome everybody to the Office of Undergraduate Research Education Series. Today's presentation is on Seeing Through AI, and our speaker is Dr. Shireen Elhabian. This is a virtual event and it's being recorded, so we ask everyone to mute yourself and turn off your camera to ensure the best experience. If you have any questions, please use the chat feature or unmute yourself when invited by the speaker. And this is the event evaluation QR code, and I'll also put the link in the chat. We would love everyone to complete that after the presentation, but we want to remind the Europe and Wilk scholars that you must complete the evaluation in order to receive credit for attending today. And the mission of the Office of Undergraduate Research is to facilitate and promote undergraduate student faculty collaborative research and creative works in all disciplines throughout the U campus. And we would like to acknowledge that this land, which is named for the Ute tribe, is the traditional and ancestral homeland of the Shoshone, Paiute, Goshute, and Ute tribes. The U recognizes and respects the enduring relationship that exists between many indigenous peoples and their traditional homelands. We respect the sovereign relationship between tribes, states, and the federal government, and we affirm the U's commitment to a partnership with Native nations and urban Indian communities through research, education, and community outreach activities. And now I'd like to introduce today's speaker, Dr. Shireen Elhabian. She's an associate professor in the Kahlert School of Computing.
Thanks, Shelley. Welcome, everyone, and thanks for being here. Today's talk is called Seeing Through AI, and that title means two things. First, we will look at how AI-powered systems actually see, how they interpret digital images, learn features from data, perform tasks, imaging-based tasks. But we will also look at something more deep. What does it mean for us to see through AI? To examine the use of AI critically, how do we trust these systems, especially in high-stakes environments? So whether you are here with a research interest or artistic curiosity, or just want to better understand the technology that is being shaping our future, this talk is for you. But before we get into AI, I want to start with something very simple, a few images that actually matters to me. This is a photo of me with my students capturing a moment of excitement about having my first PhD student defending her dissertation. And here we are at a conference in Vancouver. It wasn't just a good picture. It's a memory of shared excitement of presenting work we believed in and stepping into a broader scientific community. And this one is a graduation moment. This image marked a culmination of years of effort, mentorship, and growth. They are deeply personal and part of this broader story of education and research. And yes, those were personal images, ones that are full of memory, meaning, and milestones. But actually, digital images are everywhere. They are doing far more than just preserving our memories. These are also images. They don't capture people or celebration, but they tell stories all the same, either about health, the environment, security, structure of the matter itself, from CT scans to fingerprint sensors to infrared cameras, self-driving cars. All these are digital images. They are constantly being created, collected, and analyzed every day. And what's powering much of that analysis today is AI. So let's take a look at what does it mean for a machine to see and why it matters. But I want first to start with telling you why this piqued my curiosity to start with. So humans have an incredible, almost effortless ability to interpret complex visual scenes, often using prior knowledge, intuition, and even unrelated experience to make sense of what we are seeing. That ability, the way that we quickly make sense of messy, blurry, unfamiliar images, is what first drew me into the world of medical imaging and AI. Over 2 decades ago, I found myself working with very noisy microscopic images. The ones that you're seeing here are even cleaner versions. These are like more than 20 years ago, so I can't have even an access to these kind of noisy images. And at that time, I realized how quickly, even though I haven't had a chance to see a microscopic image before, I was quickly able to recognize patterns and structures. It was fascinating for me, not just because I can do it, but it actually opened my eyes to, okay, how we can teach machine do the same. Could we automate such kind of perception or even go beyond what humans can do? That's when I began focusing on data-driven approaches for image analysis and eventually on AI. Now that we have seen where images appear in our lives, from personal moments to scientific tools, let me talk about how machines actually see and understand images. Here's a fun example, hopefully to break it down. Imagine this image of a cat, or even a cat, or even any other kind of animal. And we want to ask, what exactly does a machine need to do with that image to mimic our visual system? At the simplest level, it might just need to recognize what is in the image. This is called classification task. The model says, this is a cat. There's no location, there's no shape, it's just the presence of the object. If we want to go a step further, the model can actually say to us where the cat is in the image. And this is what's called localization task, drawing a bounding box around the object of interest while identifying it. Now let's add another level of complexity. There are multiple objects, a cat, a dog, and a duck. And we want the model or the AI system to find all of them and actually to classify them. And this is called object detection, finding and labeling multiple instances in the scene that we are seeing. And finally, we can even get really detailed, outlining the actual shapes of each object, not just boxes. And this is called, in AI, called instance segmentation. It doesn't just detect the dog, it actually tells us where the dog begins and ends in pixels. These are just a few core tasks AI performs when analyzing and interpreting images, and each one requires increasingly sophisticated ways for machines to interpret visual data. While the dog and cat example is fun, in my work, I apply these same exact tasks, but to medical scans, cellular images, and 3D biological data, where understanding the image is not just helpful, it can be critical in helping doctors and clinicians make quicker and more precise decisions. And I'm not sure if you have picked that up, but this image, this is stylized rendering of a human body, was actually generated by an AI. I used it here, not because it's perfectly accurate, because it's not, but because it is surprisingly effective at communicating structure, at communicating my point. And that raises an interesting point. When we use AI to create content, if even images like this one, how do we give credit? How do we cite it? And more in research, education, and publishing, we are not just consuming AI-generated content, we are integrating it. That brings up important questions about authorship, about attribution, and responsibility. We'll come back to these questions later, especially around the ethical AI use, but for now, just know, yes, even images like this should be cited, ideally with the tool that you use to generate the image, the date, and sometimes even the prompt that generate that image. In my lab, we develop algorithms and computational methods to help clinicians and biomedical researchers analyze images faster, more accurately, and with minimal expert intervention. Our goal isn't just to build high-performing models, but to design systems that are practical, accessible, efficient, and also reproducible, tools that can actually be used in real clinical and research workflows. At the core of my research is one driving question. Can we help doctors see what the human eye cannot see by using AI to go beyond what's visible? That question has shaped my work over the past 2 decades, and it also reflects the evolution of AI in medical imaging more broadly. Remember our cat, dog, duck kind of example? Now let's see how that fun visual maps onto real medical challenges. The same tasks, but it's just higher higher stakes. Before we talk about how AI has evolved in this space, it's important to understand why even medical imaging is such a powerful tool and important domain for AI. Imaging data itself amounts for nearly 90% of all healthcare data, far more than lab results, clinical notes, or even billing records. These images, MRIs, CT scans, ultrasound, and X-rays contain tremendous amount of information about the body's structure and function. They are used in almost every stage of care, from initial screening and diagnosis to treatment planning, surgery, and follow-up. Here you can see how imaging plays a central role in assessing, for example, the cardiac function, or identifying bone and joint abnormalities, or guiding interventions like in atrial fibrillation when they wanted to ablate regions in the left atrium that actually causes irregular heart rhythm. Because these images are so much data rich, and because clinicians rely on them for critical decisions, they are ideal targets for AI, which thrives on complex data and pattern recognition. So now that we see how essential imaging is to modern healthcare, let us look at how actually AI has grown from the early days till now, from early tools with limited power to intelligent systems that we are hoping to integrate into clinical workflows today. Over the past 2 decades, we have witnessed a dramatic transformation. In early 2000s, AI was largely experimental. Models could identify some obvious patterns like spotting fractures or tumors in X-rays, but they were very constrained by 2 major factors: limited computing power and lack of data. Back then, most systems were rule-based. They followed simple if-then logic. These were hard-coded, rigid rules and didn't adapt over time. By the 2010s, we entered the era of machine learning. These models could learn from data, but still relied heavily on handcrafted features. Experts had to decide what to extract from an image in order to perform a specific task, then train a model with those features. Now, with modern deep learning, we have entered a new phase. These models learn directly from raw data without telling it what to learn from it, often outperforming traditional approaches. They can detect complex, subtle patterns that are sometimes invisible to the human eye. With all this progress, AI detecting disease, predicting outcomes, or even assisting with treatment planning, it's natural to pose and ask, what does this mean for medical experts? If AI can do so much, where do humans fit in? Do we step aside? Do we partner with machines? Or do we risk being replaced entirely? These are important and very human questions, and they are especially urgent in fields like medicine or any kind of high stakes environments where expertise, judgment, and trust are central. Let's take a moment to address this. So let me be clear here. AI is not about replacing our medical professionals. In fact, the most impactful uses of AI happen when it works alongside with clinicians, not instead of them. Here we show a typical medical workflow. A radiologist interprets imaging data, writes a report. That report helps the physician define a diagnosis and a treatment plan, and later a follow-up imaging might be used to evaluate the success of intervention. AI fits into this workflow not as a replacement for human judgment, but as a supportive tool. It can flag abnormalities, it can prioritize urgent cases, it can quantify subtle changes or suggest possible diagnosis, all of which can save time and reduce cognitive load for clinicians. That is especially valuable in overburdened healthcare systems where radiologists may be reviewing hundreds and hundreds of images every day. So the role of AI here is to enhance efficiency, reduce variability, and support better decisions, not to take over. Being able to build AI systems, even powerful ones, isn't the whole story. There's a growing need to step back and ask a different kind of question. What does it mean to build and use AI in a responsible manner? That brings us to one of the most important topics in the space today, AI and ethics. Because as we integrate AI into research, education, medicine, and daily life, we are not just designing algorithms, we are making choices that affect people. In high-stake environments, such as healthcare, for example, it's not enough for AI to be impressive. It's not enough to be powerful. It has to be responsible, meaning that it behaves consistently, avoids doing any harm, and earns trust of the users. This is what we mean when we talk about responsible AI. So if we want AI to truly help, not harm, especially in high stakes areas like healthcare, we have to ask, how do we know we can trust it? That's where the idea of responsible AI comes in. It's not just about accuracy. It's not about whether the system behaves in ways, it's more about whether the system behaves in ways that are fair, transparent, robust, and respectful of privacy and sustainability. So let me walk you through this. Ethics of building AI has mainly four primary pillars. First, we need fairness, making sure that AI works equitably, across different populations. It doesn't amplify existing biases in the data sets. That means we should audit models for bias across race, age, and gender, and ensure that when we build these kinds of systems, they have to be trained on diverse representative data so that the AI system doesn't propagate any kind of biases coming from the data. The other pillar is transparency. Do we really understand how the AI system reached its decision? Can a human interpret or audit its reasoning? In this case, this brings a huge body of work in literature that builds on how explainable and interpretable these models are, using, for example, visualizations and reporting tools that actually help users see what triggered a specific decision as an output of an AI system. Next is robustness. Will the system perform well when the input is not perfect? When the input doesn't resemble any kind of training data that has seen before? Can it handle unusual cases, noise in the data? And this brings up as we build these kinds of systems, they have to be stress tested on edge cases, on noisy inputs, on rare scenarios, not just ideal preserved cases. And finally, privacy and sustainability. Are we really protecting sensitive patient data? Are we mindful of the environmental cost of training these kinds of models? And in terms of privacy, we anonymize sensitive data, although the anonymization has to be very deep because sometimes patient information can actually be engraved intentionally or even unintentionally in the images themselves. So it has to be, it is a very hot topic in research. We also have to follow best practices in terms of data security and make smart choices about how high compute models are truly needed. These principles altogether are not just nice to have things, they are design choices. They shape how AI systems are built, tested, and deployed. And they are the foundation for making AI that we can trust and responsibly use, especially when lives are on the line here. So far, we have talked about building trustworthy AI systems, but there's another side of that conversation. What is about how we use AI, how we can use it responsibly, especially when we're talking about education and research. Let's walk through some of the key ethical questions that are coming up more and more as these tools become integrated into our everyday work. The first, who gets credit, authorship, and attribution? When we use AI to generate text, images, videos, ideas, who is the author? Is it the person who wrote the prompt? Is it the model? Is it the team that trained the model? And to be frank here, there is no universal answer for this yet. But a good rule of thumb is, if AI contributed significantly to what you have created, disclose it. And don't claim full authorship without acknowledging the tool that you have used. Second, transparency. Whether you are writing a paper, preparing a figure, submitting a project, it's important to be transparent about whether you have used AI and what is the level of AI involvement in this product. Many journals and conferences, for example, now ask authors to state whether generative AI tools were used and how they were used, and that level of openness starts to build the trust among the community. Third is about, can we trust the output? Which brings me to hallucination and biases that can be produced by these kinds of systems. AI does not always tell the truth. And I will give you a very fun example in a bit. In fact, it can generate confident-sounding text that is completely wrong or reflect harmful biases that exist in the training data. So even when AI helps us draft or explore ideas, human judgment and verification remains essential. Next is environmental cost. How sustainable is it? Training and running large AI models consumes a lot of energy, sometimes even more than training a human graduate student over several years. While this is not always visible to end users, it is worth asking, are we using AI efficiently and only when it meaningfully adds value? And the last point that I want to add, who controls AI? Finally, not everyone has equal access to these tools. Many of the most powerful models are owned by a handful of large companies, raising questions about data control, economic access, and academic freedom. This is why open source AI and responsible regulation are becoming hot topics in both policy and research community. And let me wrap this up. As users of AI, we are not just passive consumers. We are also stewards of how these tools are used and shared. Being mindful of these questions help ensure that AI becomes a tool for good, not just a hype or trend. So far, we have talked about how to build ethical AI systems and how to use them responsibly in research and publishing. But how about classroom? How about education? How about your own learning? Let's talk for a moment about how to use AI as a tool, not a crutch, in education. AI can incredibly be helpful for brainstorming ideas or clarifying concepts you are struggling with, much like you would use a tutor or a search engine. But when you rely on it to do the work for you, like solving an entire assignment, you actually are missing the point. Learning only happens when you engage with the material itself, by yourself. Here is one way to think about it. AI is a lot like a calculator, a sophisticated one, I guess. It is great for checking your work or helping you explore different approaches. But if you don't understand the concepts behind the numbers, the tool itself cannot help you much in the long run. In other words, it's only useful if you already know what you're doing. And here's a funny example. A reality check. A generative AI tool can be useful, but they are far, far, far from being perfect. They can produce confident nonsense, like this example of, or even fabricated sources and data or answers. So it's not just about using them ethically, it's using them critically. Always ask yourself, does this make sense? Can I verify it? Regardless of the tool that you're using, these tools are becoming, or the models, I guess, are becoming more and more powerful every day. But it always comes with, do I trust this output? So you have to verify the output first. So if we treat AI as a thinking partner, not as a shortcut to do your tasks, we not only protect our own learning, we also make sure that these tools are helping us to grow, not replacing the thinking we actually need to do. And that's how we make AI a tool for good in research, in learning, in education, and in the future of our professions. Okay, let me get back to imaging. So far we have talked about what AI can do and how we make sure it does it responsibly and how we can also use it responsibly. Now let's step back and ask, okay, what exactly is AI working with when it analyzes images? What is an image to start with from the computer's point of view? And what kind of tasks do we teach an AI system to perform? Here are more examples of images used across very different domains, like thermal imaging, MRIs, stereo images, or even radar images. At the first glance, they look completely different. And in terms of what they show, yes, they are vastly different. Some show temperature, some show structure, some show density or depth. But here's the key idea. Despite the different content, these images all share the same underlying structure. They are all data organized in a spatial grid. Each image is essentially a grid of values, whether it is brightness, intensity, color, or something more abstract. And that means we can often apply the same exact techniques across fields, from medicine to climate and urban climate science and urban planning. So whether we are identifying tumor, tracking a wildfire, or reconstructing a 3D model, the computational tools often speak the same visual language. So what exactly is the shared visual language? At the heart of almost every image, whether it's a fingerprint or satellite image, or even a brain scan, is a spatial grid of data values, which are called pixels in 2D or voxels in 3D. So what may look like a smooth theme to us, like this image here, is actually just a grid of numbers when seen through the eyes of a machine. And here's how it works. You start with an object in a real world, say a teapot or a human body, and a sensor, whether it is a phone camera, a CT scanner, a satellite, it captures the object as a grid of intensity values, and that's your image. The units might be brightness, depth, temperature, density. The data values vary, but the form stays the same matrix of numbers. Here in this zoomed view of a pelvis scan, it's a grayscale medical image that becomes a sea of floating point values, just numbers that reflects the response of the bones to the X-rays in a CT scan. That's what AI sees. And we can teach it to make sense of it. It sees a bunch of pixels, and teaching an AI system means how to move from an array or a grid of pixels into a decision or into a semantic information about what is in the image. Okay, let's start with one of the most common image analysis or AI imaging-based tasks, which is called classification. At its core, classification is about teaching a computer to look at an image and decide which category it belongs to. So like this, is this a dog image or a cat image? The AI looks at patterns in the data, tries to learn boundaries that separates different classes. Now, let's take that same idea into a much critical context like pathology. Here, we want AI to classify whether a tissue is normal or shows sign of tumor activity. This is based on microscopic patterns that human pathologists are trained to recognize, but AI can also learn from large data sets to recognize such patterns. Or consider inflammatory diseases. Here, AI can be trained to classify the severity of tissue inflammation by comparing new samples to labeled samples, assigning, let's say, a score of severity based on the given image. AI can also automatically detect or identify different types of blood cells, which can support early diagnosis and monitoring of various conditions. All of these are examples of what is called computer-aided diagnosis, or CADX, where classification helps experts make better, faster, and more consistent decisions. Once an image is acquired, one of the most important early steps in image analysis and understanding is open segmentation, which simply means identifying and separating out the parts of the image that we care about. So here's a visual example. In this image, it's an urban scene. Segmentation helps us helps the computer actually, to outline where each object begins and ends, separating, let's say, people, vehicles, and background. And the goal here is to separate what we call foreground, which is the objects of interest, from the background, which is everything else that we're not interested in. This same process applies in microscopy, for instance, where segmentation helps separate individual cells or nuclei so that they can be counted or classified or even tracked over time for disease, for understanding disease progression or treatment response. In medical images, segmentation also identifies specific anatomical regions, like in brain images, for example, or isolate abnormal tissues in pathology slides. So these regions can then be measured or further analyzed for disease diagnosis. So segmentation is often the first step in a more advanced tasks like classification, tracking, or even 3D reconstruction. Because before you can understand an object, you have to define where it is and you have to classify it, of course. That brings me to the detection task. It's another core task in image analysis, and it comes into two main forms. Either you detect the object or you get specific landmarks of interest. So in object detection, the goal is to find and label individual objects in an image. like faces in a crowd or tumors in a CT scan, the model basically draws a bounding box around each object that it identifies, often with a confidence score, how confident the system is. This is widely used, for example, in security systems, to self-driving cars, also in healthcare, because it's mainly the vehicle that powers the computer-aided detection systems. Landmark detection is a bit more precise. Instead of boxes, it actually tries to find key anatomical points that clinicians or physicians are interested in, like, for example, bone joints, teeth, or even curvature of the spine. These landmarks are crucial to measure, for example, growth, to track deformities, to plan surgeries, and so on. It's widely used in orthopedics and dentistry, and like object detection, is often the first step before applying other types of analysis or making clinical decisions. In many cases, the images that we work with are not perfect. They may be blurry, they may be noisy, low resolution, or just incomplete. That's where the whole field of image enhancement comes in. Using AI to improve image quality, or even generate missing information from the images. So, for example, here we see an example of super resolution, where a low resolution image is enhanced to recover sharper details. This is useful in surveillance or video restoration, or even improving low resolution medical scans for better quantifications. There's also the denoising task, which is basically reducing the noise captured, whether this is coming from the sensor noise, or any kind of noise that actually prevents relevant features to be extracted from the image. Think about an MRI or a microscopy, where high sensitivity often means noisy images. So denoising helps preserve clarity without losing crucial structural details. Another example is what's called image translation or synthesis, or in today's language, generative AI, where you generate actually images from another images, or image translation sometimes, where we use one image to try to predict another image conditioned on the input image. For example, here we can translate an MRI scan into a synthetic CT scan, which could reduce the need for additional radiation exposure during diagnostics. This is the image on the bottom. This shows how we can adapt one scene into another context. Here, translating a daytime image driving scene into a nighttime driving scene. All of these enhancement techniques help us get more value out of the data that we already have, making AI not just a tool for analysis, but also for improving the quality of what we see and what we acquire. Okay, so far, we have seen what AI can do with images, but this raises a big question. How does AI actually know how to do all of this? The answer lies in a powerful concept called machine learning, the core or the engine behind most of today's AI systems. So let me give you a very high-level view of what is machine learning. Humans are naturally great at learning from experience. Give a child a few examples of cars and bikes, and pretty quickly, they will be able to tell them apart, even if they have never seen such images before. They don't memorize every possible bike or car. Instead, they learn patterns, wheels, frames, shapes, motion, and use that to make sense of new examples. So machines can now do something very similar. Instead of hand coding what makes a car different from a bike, we give the machine lots of labeled images of cars, images of bikes, and it learns those patterns directly from data. This is the basic idea behind machine learning, not telling the computer what to do step by step, but letting it learn from experience, just like we do. So rather than being explicitly programmed with the step-by-step instructions, machine learning models learn patterns directly from data. This captures one of the most important shifts in how we approach problem solving with computers. In traditional programming, years ago, humans write explicit rules, a set of instructions that take in data, produce an output. For example, we might write a code to say if the object has two wheels, and handlebar. We call it a bike. But in machine learning, we flip this around. We feed in a lot of data and examples of correct output. And the machine figures out from the data these kinds of rules or the program on its own. So instead of telling the machine what a bike is, we show it thousands and thousands of labeled images. These are bikes, these are cars. And it learns the features that identify or discriminate bikes versus cars, or a bus versus a motorcycle. This is the core idea behind machine learning. The machine learns from experience, and this experience is coming from labeled data. It builds its own internal model to make predictions on new unseen data. So now that we know machines can learn from data, how does that actually happen? So let me give you an overview of a typical workflow of building a machine learning model. It all starts with data. It could be images, numbers in a spreadsheet, or even text documents. For what's called supervised learning, which is what we are focusing on here, this data also comes with labels, like whatever output that you would like to do. If it's a segmentation, for example, if it's an image segmentation, it will be the segmentation of the different object of interest that we have in the images. For example, if it's a diagnosis task, it will be images or even clinical notes and the underlying diagnosis. So the machine will use these examples to learn. Then next, we feed this data into a learning algorithms. Often a model like a neural network, you can think of this as a system made of layers of nodes that mimic how our neurons in the brain might actually process visual signals or any kind of input signals. The model analyzes the input data, starts to identify patterns, which pixels tend to belong, for example, to cats versus dogs, what kinds of shapes belong to dogs, or how certain variables predict a specific outcome. This is called training phase, where the model adjusts its internal state based on what it sees in the training data, trying to reduce some kind of error to improve accuracy over time. Once training is complete, the model is ready to make predictions or classifications or even segmentations, and you can give it a new input that doesn't belong to the training data, like an unlabeled image, and it outputs a prediction. This image looks like a dog, or this patient has no tumor. This is what's called inference, and using the machine learning model that has been trained to make decisions on new unseen data. And here's the exciting part. The system can keep improving. When it starts to make errors on new data, we can actually improve it over time. We can feed its prediction back in and add new labeled examples, and refine the model to get even more and more accurate over time. This feedback loop is key to building smarter and more robust AI systems. So in short, machine learning is all about learning patterns from labeled data, training a model, and using that model to make predictions and decisions just like we do, but only at a scale. So when we say we are training a machine learning model, what we are really doing is helping the model learning a relationship, a mapping between input and output. For example, if we are working with image data, the input might be a set of pixel values. The output might be a label like a dog and cat. And during training, the model sees many examples of input-output pairs and learns the patterns that connects them. The goal is that once the model has learned this mapping well, it can take a brand new unseen input and make an accurate prediction. And even though it never see that exact example before, it can generalize to it. This ability to generalize from past examples to new situation is what makes machine learning and AI built on top of machine learning very powerful. And that's and why it is now at the core of so many systems, including image analysis systems. And to be frank here, AI models are as better or as best as their training data. the better the data and the training process, the more accurate and trustworthy these predictions will be, which is especially important when it comes to high stakes environments like healthcare or science. To wrap this section up, I will leave you with one of the most widely quoted definitions of machine learning from Tom Mitchell at Carnegie Mellon. Machine learning is at its core the study of computer algorithms that allow computer programs to automatically improve through experience. In other words, instead of coding every rule by hand, we give the machine experience, data, and it learns from it, improve over time. This idea of learning from data is the heart of all the modern AI systems and is what makes today's image analysis and computer vision tools so powerful and adaptable. Now that we have seen how machine learning works, it is important to note that not all AI systems actually learn or adapt over time. Some systems already use predefined rules, like this example of rule-based AI, where a system follows an if-then logic. It's an AI system, but it is not a learning-based AI system. For example, if someone has a fever and they are coughing, then diagnose this as a flu. These systems do not learn. They don't use data to adapt. They follow a fixed decision tree written by humans. Another type is symbolic AI, which uses formal logic to reason through problems. Chess engines, for example, like Deep Blue, fall into this category. They don't learn from experience. They explore many possibilities using pre-programmed strategies. And then there is this heuristic AI, which uses shortcuts or rule of thumbs to solve problems efficiently, like A-star algorithm for finding the shortest path through a maze, for example. Again, no learning involved. It is clever, but it is static. So while today's focus is on machine learning and AI that improves with data, it's worth remembering that not all AI is learning-based. Some systems are powerful, but just operate on fixed logic, not experience. That brings the question, when to use which? So now that we have seen this difference between learning and non-learning AI, a natural question arises, when do we use which? Non-learning AI is still powerful, is still very useful, especially in environments that are stable, well-defined. Think of counting systems or traffic lights. Accounting systems or traffic lights. They don't need to learn. It will be even an overkill to train an AI model to perform the same tasks as a calculator. We just want them to follow fixed rules accurately and reliably. They're also great for predictable tasks where we already know the logic, and for situations that are less data intensive. If we don't have data to train an AI system, well, better to use a non-learning AI, where collecting data or large data sets might be either not practical or not necessary or even not feasible. But when the environment is complex and constantly changing, or when the system needs to adapt and improve over time, this is where learning AI comes in. This includes things like medical image analysis, autonomous driving, recommendation systems, and real-time language translation, all of which benefit from being able to learn from new data as it comes in. Okay. This will be my last section. Hopefully we'll have time. So now we understand what machine learning is and when it is useful. Let's take a step back and look how actually we got here. Was AI really there from the very beginning? And the answer is no. AI didn't replace traditional image analysis overnight. It evolved out over time from being really limited to being so intelligent. So let's look at how machines used to see images and how deep learning changed everything. Before the era of AI, image analysis followed a very manual, structured pipeline. We would start with raw pixels from an image, process them to reduce noise, to enhance contrast, then extract the specific handcrafted features, things like edges, corners, or shapes, and finally use those features in an analysis task like a classification or a measurement. So let's zoom into the first step, image processing. This is about preparing the image by improving quality or adjusting for lighting, orientation, or scale. These adjustments help highlight relevant features before any kind of analysis happens. One kind of transformation is called intensity-based transformation, where we adjust pixel values to enhance the visibility or make certain features stand out. Like, for example, improving in contrast in an image, or enhancing the appearance of vessels to become easier to spot. Most of these operations use simple mathematical functions applied usually pixel by pixel. Think of it as a changing the brightness or contrast at each point individually based on some predefined rule. But sometimes we need more than just changing individual pixels. We need to reduce noise, find edges, and highlight boundaries. These tasks require context, require not only the image, but also surrounding pixels. And to handle these cases, we use what is called the image processing image filtering, where each pixel is updated or computed based on some form of a neighborhood or pixels surrounding it. This allows us to do things like image sharpening, noise removal, even blurring the image or enhancing the edges of the image. Besides adjusting pixel values, we also sometimes shift the spatial layout of an image, like rotation, translation, scaling. These, what's called geometric transformation, help align and compare images. So here are some examples of geometric transformations. These are often used for aligning scans from like different time points or even different patients to be able to compare one scan to the other. Once we have cleaned up the raw image using different processing techniques and pipelines, the next step is to extract information from it so that we can use it to perform the downstream analysis task. This is where feature extractions comes in. We look for patterns, structures, and we here are actually human is looking for patterns, structures, and characteristics in the images, such as shapes, edges, or texture that would help us describe what we are seeing in a way that is useful for a downstream analysis. These features act like clues that help the computer understand what is in the image even before any AI is involved. Let's look at some of these features more closely. We can use, for example, color. Finding a specific colored car in a parking lot. Texture can also help tell us whether a surface is rough or smooth, like identifying a tiger's fur pattern. Shape plays a big role, where we might expect, for example, a football to have a specific geometric shape, or a lizard would have a specific geometric shape. Motion, identifying moving object against the background, can also be a useful clue for real-time imaging. All of these are features that we identify as humans, and we code actually or program computers to look for these kinds of features before even doing any kind of analysis. However, not all features are useful all the time. In this image of a plane in the sky, texture doesn't help much. The sky and plane are very smooth. What is more useful here is combining shape and motion to identify this plane in the sky. So in traditional workflows, choosing the right combination of features is a key and often require expert judgment and a huge, significant trial and error process. However, this reliance on hand-designed features has a lot of limitations. These features are often not enough to match the nuanced understanding of a human being, and they depend heavily on domain knowledge, meaning that we have to guess what kind of features we might to look for a given task, and it's not always the case that we are correct. Worse, the design of these features are actually separate from the task itself, so we couldn't always be sure whether we are using the best set of clues from an image. And this is where AI, especially deep learning, changed the game. Instead of manually designing features, we can now let the model learn the features directly from data. Just give it enough data to label data to learn this mapping from input to output. These systems are often referred to as black boxes because we don't actually see what is being learned, how they are learning it. But what we do know is that they can discover highly complex and subtle patterns that even human might overlook, and that are perfectly tuned to the task at hand because it has learned this mapping from um, the input raw images without even pre-processing to the task of interest. So this diagram shows what happens inside a deep neural network that is used for image analysis. The image goes through many layers. Each layer learn different level of abstraction. Each layer, like for example, early layers detect edges and colors. Deeper layers more recognize shapes and texture. And final layers combine all of this to make a decision, like for example here about identifying a traffic sign. This feature extraction and classification rolled into one big unified process, and all of them are being learned from data directly. This is what makes AI so powerful in visual tasks today. But there is no free lunch. As powerful as learning-based AI can be, it doesn't come for free. These systems are incredibly data hungry. And what we are talking about, like high quality data, especially for tasks like image classification or image segmentation, or any kind of AI, any kind of automated task that we would like to perform on images. For example, in natural image domains, data sets such as COCO, ImageNet, we have access to hundreds of thousands of annotated data. These can often be crowdsources because these are natural images. I can give it to someone who do not have any kind of experience, and they can annotate or segment them. Thanks for their simplicity and their widespread familiarity. But for medical imaging, it's a different whole ball game. The labels are hard to get, often sparse, not sometimes, most of the times, noisy. Here we need an expert, a pathologist, a radiologist, someone who actually understands what they're saying to label tumors, to label organs, subtle signs of disease. That level of expertise is so expensive and not easily scalable. And even with experts, labeling can be inconsistent, especially for complex or ambiguous cases. This means we must be careful not to take training data for granted. We have to really quality control this kind of data. And it is often the biggest bottleneck in building reliable AI systems in healthcare. In many non-medical domains, open and standardized data sets like COCO and ImageNet have transformed AI by enabling fair benchmarking, widespread collaboration, and rapid model development. But in medical imaging, we face a very different landscape. There are major hurdles around patient privacy, data sharing, standardization. There's no single medical ImageNet and probably never will be. Even within one hospital, the data can vary depending on the scanner, the protocol, or even the patient population. And when you go across in different institutions, the variability even becomes more pronounced. This makes it difficult to train robust models that generalize as well. Without consistent, accessible data sets, progress in AI for medicine becomes more challenging, but are more important to do it right. As of now, the field is moving towards having like larger scale public data sets for evaluating different AI tasks on medical images, but it's still in its early stages. No matter how many public data sets that you can find out there, it's still in its early stages. So let me wrap up. We have seen how AI has transformed what's possible in medical imaging. In specific, it can help detect disease earlier. It can help in personalized care and support clinical decisions in ways that we never could before. But we have also seen that it's not a magic pill. It's a data-driven, often opaque, and deeply dependent on how it is being designed, trained, and used. As future researchers, clinicians, students, or just informed citizens, it is up to us to ask, are we using AI responsibly? Are we including the right voices? Are we staying aware of both the possibilities and the pitfalls of building and using these kinds of systems and using them in high stakes environments. Because ultimately, AI is not about replacing people. It is about empowering us. And when it comes to something as important as health or science, or any kind of high stakes environments, that is a responsibility that we all share. So I will leave you with these key takeaways. This image has been generated by ChatGPT just before the talk. So yeah, maybe most importantly, just stay curious, stay creative in using these kinds of tools to do the good, and to help you grow and to help you learn and explore ideas, but always don't trust their output, no matter what model you're using. Don't trust them. You have to use your human judgment. It's not about replacing us. It's about augmenting us.
Want to remind everybody about the evaluation form. I just put the link in the chat. But remember, the Europe and Wilk scholars must complete this in order to get credit for attending today. And we just want to remind everybody that the Office of Undergraduate Research, we're in the SIL Center, which is just east of the Union parking lot. We're open Monday through Friday, 8 to 5. Our website is our.utah.edu, and you can email us at our@utah.edu. And thank you again, Dr. Elhabian. We appreciate this presentation. It was great. Thank you.
It was a pleasure talking to everyone. Thanks for joining.